talking about the Fast and Furious paper. This is real-time 3D detection, tracking, and motion forecasting with a single ComNet. This is actually something. This is similar to I guess you can think of a brief overview of this. This thing I think of something similar to the ChauffeurNet, and it's also you can also think of it somewhat similar to the behavior cloning project that you've done for Project 4. However, this is in 3D. So yeah, I had overview of, I read through this paper. I can't say I understand everything, but one thing you do take away from after reading a lot of these papers is that the people who write the papers, they have spent weeks or months even to working away on these findings, and when it comes to time to explain the findings, it's not always going to transfer, to the way that to a way that is very explainable or easy to explain. And often there are a lot of big words in here. There are things like holistic, which I actually had to look up because I haven't heard the term for holistic in a while, but yeah, that's essentially what happened. Anyways, let's go through paper. Okay. Detection, typical, and I'll put faster motion forecasting. And red light, okay, in contrast. Yeah, so generally, what is the paper is stating is that a lot of the detection, tracking, and computer vision, etc. A lot of these pipelines are there are several pieces to it. So there is a detection, there's object tracking. So detection, you can think of like your computer vision, your lidar, radar, sensor, and all that. Object tracking is you're tracking where the different cars and pedestrians and motorists, etc., where they're going, where they are. Motion forecasting is this part is you're forecasting where they are moving and if they're going to collide into you and all that, right? So each one of these usually have their own pipelines. The approach of this paper is that they take everything together and they use one ComNet to do both all three of these: one detection, object tracking, and motion forecasting. And what they do, what's particularly different about this paper is that they use 3D data as opposed to just imaging. And these 3D sensor data usually are fed back from, say, either radar or lidar. Get a point cloud, and you can use that. The framework described here uses that 3D data to do the detection for object tracking and motion forecasting here. Right? So they take advantage of 3D sensor and design network that takes a bird eye view of 3D world and represents 3D nature of the sensor. So you can see actually this is actually shown in bird's eye view. One of the examples done by a student that was from a former project. I believe it was a former project 5 of term 1 was actually vehicle detection, and vehicle detection back then was using the images, and most of us did a 2D detection, but one student did he did a bird's eye view of the image, and he took that and then he mapped into a 3D detection. It was pretty amazing, but there you can think of this as a similar of like a similar concept, except now you're using 3D data instead. So as you can see, there is a lot of advancements that's being borrowed from previous work. So this application is one stage detector takes 4D tensor. So you can think of it here like you have 3D, and if you add time to that, that will be 4 dimensions, right? Because you have one frame, one time frame, you have 3D, you have a set of 3D data, and then onwards you have an array of those that makes a 4D tensor. And the tensor is essentially anything that is beyond 2D of space and time interact accurate bounding boxes. Yeah. So the bounding boxes produce bounding boxes on current frame. So it's multiple time frame in the future, and then using that, they can create a tracklet from these predictions. For operators like find evidence from past and current prediction. Okay. So I believe the paper just covers the more interesting part where they do these 3D detections, because this is like the meat of the paper. Yeah, I didn't see too much about the tracklet, or it was harder to understand the rate. We demonstrate effectiveness modeling in a very large scale data set that of course significantly outperforms state of the art, and actually it runs very fast in 30 milliseconds. There's a lot of related work. You can see some of the mentions are here, like regional proposal network, which is our RPN, and then there's YOLO SSD. So this is for 2D object detection, 3D object detection. You can see, let's see, this is related work, right? So image detection, 3D detection, point cloud, 3D convolution voxel. So voxels are just essentially like you can think of 3D blocks. So so these 3D blocks are yeah. So this is what it looks like. It's kind of hard to explain, but that's essentially what's representing what they meant by voxels, right? Images with FusionNet, images and 3D point FusionNet, and they did the 2D convolution virtual. Yeah, so the handcrafted height features as input comes in result. Okay. Handcrafted height features. I believe this it's really hard to understand what they meant by handcrafted height features. I'll leave it at there. So there's object tracking, right? Predation, regression, encoder, good feature tracking, seamless and perform tracking. This actually doesn't really develop for object tracking. Yeah. It actually doesn't give like a lot of detail for object tracking. Motion forecasting, patient variation. Framework proposes using recurrent for long time term prediction. So recurrent network is something that you will likely see in computer vision if you took computer vision and down degree. So for convolutional neural networks, they don't really remember they don't have concept of time, and they don't they don't remember what happened in the past, but the LCM and recurrent neural networks does do that, and this is useful for prediction and forecasting especially for complex problems, right? In theory, the interaction between pedestrian some work have found X short-term trajectory using variational encoders. I think I will leave that there. Multitask approach, right? Further, yeah, they all propose detection and tracking jointly from video. So this is already doing two things. Their work is doing three, I believe: detection, tracking, and motion forecasting. Yeah. So detection and tracking from video, then displacement, return that, put them into object tubes during inference time. Okay, so proposed single network that takes much temporal. So this adds temporal information. Temporal information essentially is just data with time. Once you add time to data, it becomes temporal. Time performance, 3D detection, short-term motion forecasting. By the way, temporal information was one of those things that I needed to look up on. Anyways, when you are reading these papers, sometimes you do have to look those up. Also, driving. So yeah, the temporal information of time series give important cue for motion forecasting. So if you knew what happened about 3-4 seconds before, you're much more likely to know what's going to happen in the next 2 seconds than if you only relied on the current frame. Holistic reasoning, this is essentially just putting everything together, allows us to better propagate uncertainty through network, improve estimates. So yeah, this by using temporal information with 3D data, they were able to have a better result, and you can run quite fast. They did some. There was a particular way where they made it really fast, which I'll show how a bit later on. So 3D detection motion forecasting, right? Right. So this is going into their work, right? They're focusing on the detection object by exploiting sensor produce 3D point cloud towards this goal with the one-stage detector, vector tracking short-term motion forecasting object trajectory. Okay, for the coding exploit 3D. Okay. So yeah, this name Fast and Furious came from the fact that they can create these estimates with as little as 30 seconds, right? All right, so this you can see the voxel representation using height directly as input feature, which I'm going to go into more. So this is where they start describing how they did the paper. Experiment in the paper in the following we first describe. Okay. And how they incorporate temporal information. All right, so this is in this section describes single frame representation of the world. So in the data parameterization, they are going to describe what at any point in time what their data will look like, right? Voxel representation. So instead of having images, they're going to have like the 3D sensory data, and these are point clouds. Um, so point cloud is essentially a point in 3D space. So you can see, of course, these aren't points anymore, but you can imagine that each one of these could be a point. And binary indication. Okay, yeah. So the binary indication essentially they're saying whether there is something at that space or not, and they assign a height to it. And so instead of doing the so what they did was instead of using whole 3D convolutions, they simply they simplified this so that the height, right? You can see these height they don't overlap. So there is something at that height, or there usually is something at that height, or isn't something at that height. This is very sparse data, so they did a 2D convolution So how do they do a 2D convolution? You can do 2D convolutions with your images, right? And if you think about images, images are let's see, 2D array with 3 channels, so that's 3-dimensional. And this is also 3-dimensional, but instead they use the height as they utilize the height as the channels instead. So this is just a very big, you can think of a very big, um, you can think of an image with a lot of channels. And it kind of makes sense because it's essentially a very detailed image with some 3D information, right? Adding temporal information. All right, so now they are adding information about the time frame, right? It's push-up consider 3D information. All right, so you can see here the 4D tensor is mentioned, right? So if you have this is 3D and yeah, actually it would be still be 4D because regardless whether you do 2D convolutions, your tensors are still 3D, so that is a 4D tensor. Let's go perform change coordinate to represent them current coordinate. Yeah, one thing they had to do is they had to shift all these 3D points and represent in the current vehicle's coordinate because your sensor is not exactly where your vehicle is. It could be a little bit behind your vehicle, so you do have to adjust for that, right? And this 3D tensor and model frame, create 4D tensor, right? Um, 3 points of hope will also give us cube ball. Yeah. Okay, so this is just mentioned that they utilize the frame utilizing the adding temporal information, how they did it and what they had to do. More model formulation, single stage 4. Okay, so they created 2 models for this. One is the early fusion, one is the late fusion. Okay, so first approach, they aggregated temporal information at the very first layer. And so because the temporal information is aggregating the first layer, right? So let's see, can produce a single point platform offering different times and differently. Here's some this, right? 40 for given a 4D tensor, we first use 1D convolution with kernel size and temporal dimension to reduce temporal dimension from n to 1. Okay, so essentially they squeeze all these time frames into one here, and we share the weight among feature maps. Okay. From convolution max pulling from VG16, layer feature map reduced by half. Note that we remove last convolution group in here. So now it's only, yeah, so the last convolution group in VGG16 would VGG16 is used for classification, so they chopped it off, and now you get your forecasting prediction, etc. It's not going to how you say flatten it into usage for classification. The late fusion does it a little bit differently. Right? So perform 3D convolution 3 by 3. There's some pro information kernel size 3 by 3. 2 branches of convolution. Okay. The second one into one frame into the future, forecasting possible approach employ multiple frames can then learn to estimate useful features such as velocity and acceleration. Okay. On SSD. This is a part where it starts getting a little bit confusing, but here you see it mentions single shot detection. So essentially, this utilizes some of the same attributes from um, SSD, which you can take a look. So single shot detection is used for 2D, but this utilizes a similar concept. See here, Redbox corresponding 5-meter real world. Okay, yeah. So after all of this, after all of this, it is mixed prediction on the bird's eye view. So you can see this is a bird's eye view. It's not a, it's not something that looks forward or in the binocular vision. This is on top, and it's going to do that. It's going to do that using a similar technique as SSD, SSD there, and yeah, all right. So decoding tracked it. At each timestamp are put detection boxes on these in timestamps. So they can aggregate this information, produce articulate track list. So you can add a bunch of these boxes together, and you can compute the track list from the boxes. Perhaps their center, etc. There's overlapping between detection from current, past, future. They are considered to be same object. Bounding boxes simply average. Okay. Into the application. Help. Particularly when we have strong prediction. Let's see. So for the aggregation, they use an average here because forecasting is not perfect. So what happens is that these forecasts are they are used together. So you can see this is a convolutional neural network. However, at the end, it still produces many layers, and each one of these layers are are detections like this. And using detections like this, so this is be like forecasting like the current. It would be like the current frame and many frames later. So you can see this box here mentioning here is that it's like that. It's kind of hard for me to go very in depth with it, but once if you have time, you can look at the code and it will make a lot more sense. Loss function and training. So what they are doing for loss function is that they are using the cross entropy loss, and the cross entropy loss are applied to these boxes on the IOUs, and let's look at this. Okay, so it's and one thing they use is a smooth L1 loss, and the thing about this is that here can you see the equation that as your loss becomes less than 1, it starts becoming not as significant because 0 point something to the power of 2 and divided by 1/2 is much smaller than the value itself, and otherwise it is more significant. And this is because, as you can see, once the loss becomes smaller than like 1, it really doesn't matter. These like 1 pixel off from like these boxes is almost like nothing. It's almost perfect. You can think of it like that. So this loss algorithm makes sense, right? And hard data mining due to inbound positive. Okay, correspond truth box negative. So they needed some. They needed some this reference call candidate. As is common, somewhat often there is no public available data sets, 3D detection structure. Collect very large scale data in order to benchmark. Okay. Because there's no so this is something impressive that they did. Um, they collected very large scale data set. They either created this or collected this in 3D. I believe this is collected actually, and a lot of people when they see that there's no existing data set, it's a really huge turn off for people who want to do stuff. Data set is collected from. So these are collected from roof mount, mentioning that they're driving around North America City. So there's over 500,000 frames collected from 27,063 scenes. Each scene consists of continuous sequence. So by the way, yeah, this is still not a lot of data. It works for an experiment to prove a point, but it's for your stuff to go into production, you do need a lot more than that. Potentially something like what they have for Tesla, Waymo training setup. So they training time, spatial X, Y region this much. Yeah, so this is essentially saying their point of view. So this is by 144 meter wide and 80 meters. Let's see, yeah, 80 meters long or in the distance, right? And each grid cell is 0.2 by 0.2 meters. That's a voxel, basically. The height dimension we take range from this, from -2. So if there's a ditch and 3.5 for anything over that is above over the vehicle, anything like really above there, unless there's some kind of pterodactyl, it shouldn't matter. So 0.2 meter interval leading to so these many bins. Essentially, you divide the difference between this by this, and you get this many bins. So that's how many categories they fall into. By the way, this is discretization. Instead of using the real numbers, you get this many bins for temporary use information. And because there's less information, this is more manageable. If you have like so many, like if you go by like 0.1 point blah blah blah, this experiment may never finish. Information, we take all the 3D points from 5 time steps. That's 5. Yeah, so they took parts of 5 frames and input 4-dimensional tensor concept time, height, x and y in both early fusion, late fusion model. So they've been training with Atom Optimizer. One thing I do have to mention is that Atom Optimizer may not always be the best. A lot of times if you experiment around a bit, you can find something better than Atom Optimizer. However, their data set is very large, so and Atom usually is a pretty safe bet, so it kind of makes sense. Generally, if you have, you should experiment with Atom, advisors other than Atom. And it took many iterations, and the learning rate was half of 60K and 80K. So I'm not sure if they manually have this, but in your deep learning frameworks, there usually is a learning rate decay parameter that you can set to slowly decay your learning rate, because as your learning algorithm converges towards you can think of the big U towards the bottom, high learning rate really doesn't help anymore, and your learning rate really should be reduced. Right. So here is so this is just going into the detection results. Right. So the way you can think of this is like at 0.5, how much of how much how many of the detections are at 0.5 IOU, 0.6, 0.7, 0.8. You can see that the FAF is doing significantly better than a lot of these, and they are. It's almost as fast as SSC, which is detection use 2D detection, and it's twice as fast as MobileNet, and it still has better results in MobileNet. So this is quite an this is quite an achievement. Ablation. Okay, so yeah, so that's what they mentioned there. So they conducted some tests to see what was important to the what was most important to the framework or their model, right? So yeah, let's see. Right. So using temporal information, early fusion it gets a 3.7% boost, and so later fusion use the same information and able to get extra improvement. Yeah. So this is better than early fusion. In addition, adding, I'm getting this is on top of early fusion, like, but I don't think they did one where the later fusion is without temporal information. In addition, adding prediction loss similar detection result on current frame alone, however, enables decode tracklets. This is also motion detection. Yeah, so detection results on the current frame really doesn't require the temporary information, but it was able to, create tracklets and make predictions and all that. So tracking, let's see, okay. For tracking, able to output detection risk directly, adding sophisticated pipeline, taps ratio, person model, output. Okay, so where's tab 3? Tab 2, tab 3, table 3. Okay. So so let's see. Yeah, so this is showing data for tracking performance. This is Fast and Furious is on par or better than a lot of the Hungarian algorithms, which I don't quite know they are. So I haven't really read into this, but you can, I mean, if you can look into that time. Motion forecasting ability, the model compute L1, L2, and L2 distance center. Okay, okay. So this is how accurate it is, and predict 10 frames and with less than 0.33 meters, and that is quite close to where the actual vehicle is. Due to the nature of the problem, they can only evaluate true positive, so therefore, true positives, which means so that's I believe that is I believe that is saying that when it believes a vehicle is there and it actually is around there. I'm sure there's a reason behind this. I can't quite think of this right now, but of course you can look at, you know, the four what you call the four I forgot, but it's like you can think of it like true positive is accuracy, and false positive is which I don't think really applies to this because the problem is just true. There's not like the false positive is almost like under this context saying that you fail to detect a vehicle, but you actually detected the vehicle. That's very hard to. I mean, you have to think about that. But yeah, figure 10 show result 100-meter region. You can see the results here. This is so I believe each one of these boxes are um either car protection. I don't believe they went extensively into the color of these. I mean, this is definitely like a big truck here. These are the cars. These I believe it could be just parked cars here. But yeah, I think that's it. One thing to mention is that you know it's not always when you read paper, it's not always about trying to exclusively understand everything in the paper. It will probably take a lot of time. I've spent about 10 hours on this, and there's still some you know some funny stuff like here that I don't quite understand. The reason being is that you at the end of the day is not the implementer of the model, so that sometimes can't be helped. But the idea is to, you know, if you see, they always list related work because the um, the the people that conduct this experiment they have went through you know related work and they borrowed a lot of the concepts from there and you know the idea is just to get exposure to what they did and you know the more you read the more you understand and with that you could come up with some ideas on you know and definitely you will learn more terms and I think that'll do it for today. Thank you.